Hello, Lecture 9, Chapter 2 about transmission lines, and this lecture is going to talk about admittance Smith chart as well as some of the feature and shortcuts that we do with Smith charts. So we'll start with admittance Smith chart. And to do so, let me remind you about how we develop the Smith chart based on the normalized impedance on the transmission line. We'll start with this expression of the impedance as related to the frequency domain reflection coefficient gamma, and then we express both the impedance as real and imaginary parts as well as gamma into real and imaginary parts, and based on that we looked at the loci of constant r and constant x, and we found these to represent circles. And those circle equations are right there, and these were the constant r circles and the constant x circles, and when we combine them together we ended up with this diagram here, which we work with in a few examples in the previous lecture. So let's get back now to our lecture material and see how the admittance comes into the picture. Here's the impedance expression that we've seen before in the earlier lecture. And basically what I'm going to do here is write the admittance expression. And the normalized admittance y sub n is going to be the full admittance, the unnormalized one, divided by the characteristic admittance, which is 1 over the characteristic impedance. So this expression here is basically the inverse of that. So being the inverse is going to be 1 minus gamma on the top and 1 plus gamma on the bottom. Here it is. So we manipulate this expression, and what do we have? We get minus gamma is equal to y minus 1 divided by y plus 1. Compared to the impedance expression that we had before, was gamma is equal to z minus 1 divided by z plus 1. The right hand side here and the right hand side there look similar. The gamma and minus gamma are exchanged here. So if I were to replace the r and x circles by the g and b circles, which are the real and imaginary parts of the admittance, I would get minus gamma instead of plus gamma. That's basically the bottom line of the admittance chart. All you need to do is just think of r and x now as g and b, real and imaginary impedance, now real and imaginary admittance, and instead of obtaining a plus gamma, you would obtain a minus gamma. So let's see how this works out. Alright, let's assume that this is our Smith chart now. And this is your r circle and that's your x circle, so this becomes your intercept point and that becomes your impedance right there, and this would be your gamma right there. If I go on the same chart and I'd like to place a minus gamma, that would be the same magnitude as gamma and would be 180 degrees away from that, so that's a minus gamma right there. So what do you think this point represents? Basically, according to this, it would represent admittance. So if this was your impedance right there, this will be your admittance value, and you can simply read the g, the real part right here on this circle, and you'd read the b on this circle right there, the imaginary part of the admittance. So that's your g normalized admittance, and this is your b, the normalized imaginary part of the admittance, or what we call the susceptance. So that was the conductance, susceptance of the same value. And you can actually use that as a complex number inverter. If you write 1 over 1.5 plus j2, guess what? You will get 0.24 minus j.32. And you can try that out on your calculator. So that is the admittance corresponding to that particular impedance value, and you would read it on the same exact scales that you use to read the real and imaginary parts of the impedance. Now let's take an example here and see how we can play out an impedance and admittance transformation on the Smith chart and make that convenient to evaluating the total input impedance of something like this. You've got sub ZL here, a piece of transmission line length L1, another impedance here in shunt, another piece of transmission line, another impedance in series, and that's where we evaluate the input impedance. So what we do is we are going to deal with each one of those as a Smith chart on its own. This part here is a Smith chart. Here's a transmission line loaded by ZL. We want to find the input impedance here. So how much is Z1 right here? And we'll go to the second transmission line problem, which is this part of the line loaded by ZP and Z1, all right, in parallel. and we would like to find the input impedance for that, which is Z3, and then we add Z3 to Zs to find the total impedance here. So there are two transmission line problems here that we're going to work on the same chart. You can work on separate charts if you prefer to, if you find that less confusing, but we're going to do it here on the same chart. So if you pay attention closely, and you may have to go over a couple of times, you will be able to see each one individually. Here are the steps that we're going to do. We'll choose a normalization impedance Z0 for the transmission line. Same Z0, because the Smith chart is designed for one Z0. It could be any of the characteristic impedances here, either this line or that line, or maybe even the input source. And then we divide ZL by the characteristic impedance, and we'll find the location of that on the transmission line, which is 0.1. So 0.1 here represents the normalized impedance of Z sub L, real and imaginary part, the way we learned before. Next, we want to move that impedance a transmission line TL1, which is a distance L1. We normalize that to the wavelength, and we decide that this is a distance moved right here. Next, we want to move that impedance, the distance L1 on transmission line TL1. So we normalize the L1 length to the wavelength of transmission line 1, and we decide that fraction of wavelength that we need to move, and then we'll move on a constant gamma circle that fraction of wavelength. All right, and basically, obviously, you are going to read those numbers on the scale that is designed for that. Right here on the outside circle, there will be a scale that will tell you how much lambda fraction that you move, and the motion obviously is towards the generator, so we're moving in this direction. So this is where we land. 0.2 is right there. So now we have the impedance at 0.2, which is right there, and I'd like to add in parallel the impedance of Z sub P, and parallel addition works out for admittances. So we need to move from 0.2 to 0.3, and that's basically an inversion of the impedance to get the admittance. So as we move to 0.3 here, by mirroring this point opposite to the center, we are getting the 0.3 here, which is still at this location, except it's now admittance. So we have that admittance at 0.3. We invert Z sub P, and then we add the two admittance to each other. We can do that by adding the two real parts and two imaginary parts, and that means you are going to move on a constant G circle when you add real parts, and then a constant B circle when you add the imaginary parts, and finally you are at 0.5, which is right here. So this is 0.5 right there, which corresponds to that location here. After adding the admittance of this Z sub 1 to the admittance of the Z sub P, you get the admittance at that location. So we can actually continue from here as admittances, but we are going to meet an impedance here, so might as well get an impedance at this location first. So at this location here, we are going to get the impedance of that point by inverting this point here, again 180 degrees, going to 0.6. So 0.6 here is the impedance of that location here. So this impedance here is 0.6. Now we're going to move on the transmission line again, but this time it's a transmission line 2, and the length is L2, and it's still towards the generator. So we start from 0.6 here to 0.7, and that's basically the motion on a constant gamma circle. Use a constant gamma circle. We'll move from 6 to 7 towards the generator, and the distance is L2 over lambda. So again, we're going to go outside here and read the L over lambda, to outside there and read the L over lambda, and that's how we moved. So we got this point here, which is 0.7 now, and that's an impedance right here. Finally, from 0.7 to the input side right here, I'm adding an impedance, which means I can add the impedance of Zs to the impedance of Z7 by again adding the real part and imaginary parts to each other, and that means I will move on a constant R circle when I'm adding the X's, and I move on the constant X circle when I'm adding the R's, and finally we land at 0.9, which is right here. So that 0.9 is the input point on the transmission line, and I can read the impedance there, Z sub n, the label. I can read the real part and imaginary part. I can read the gamma n at that location. So that's how you go back and forth between impedance and admittance to obtain the final result of a problem like this. So let's go over this whole process again very quickly. We started at point 1, and point 1 was an impedance, so here it is. And then we moved to point 2, that was a distance L1, and we moved from here to there, distance L1, and that's still an impedance. All the impedances are marked in black here, and the admittances are going to be marked in gray. Alright, from 2 to 3, I moved from impedance to admittance. So here's the same point. I move from impedance to admittance, so I have the admittance now at point 3, which is right there. Okay. Then from 3 to 5, I added a shunt admittance of the inverse of Z sub P. So from 3 to 5, I added the shunt admittance of Z sub P. I added here, the real part is added, and then the imaginary part is added. So I got 0.5. From 5 to 6, I went from admittance to impedance. At 0.6, I get an impedance that I move here a distance L2. So I move a distance L2 there to get the impedance at 0.7. From 7 to 9, I add another impedance in series. And again, I add the real part and imaginary part. So here I'm adding the imaginary part first, and then the real part next. I get the final point here, 0.9. That's the impedance at the input. So this is the input right there, and this would be gamma input. Finally, if I need to get the impedance at this location here, I read the R and X parts and then denormalize with respect to the characteristic impedance or normalization impedance that I chose here, and I find my impedance in ohms. And that is the end of lecture 9, and I'll be seeing you in lecture 10.